welcome to the second webinar organized by the ETC, Education and Training Committee. My name is Giuseppe Palmisano. I'm Associate Professor at the University of São Paulo, and today I have the pleasure, I'm co-chair with Justina of the ETC, and today I have the pleasure, together with Ben Collins, to host Oliver for this second ETC webinar of 2024. So just a few slides before starting the webinar. So the Education and Training Committee is a committee under HUPO, the Human Proteome Organization. And actually the main aim of this committee is to organize workshop, courses, tutorials, and webinars like this one that you will listen today. And we aim actually at joining all the HUPO members and all the proteomics community in and learn about cutting edge topics. So just one slide, I would like to advertise HUPO 2024 that will be in Dresden, Germany. And please visit the website. There is a very nice scientific and social program. And by the way, the first day of the HUPO 2024, the ETC will be responsible for organizing pre-Congress training courses that are courses dedicated also to different topics for young researchers, students, and so on. So by saying that, I will stop sharing my screen and I will actually now pass to Ben. Ben, the floor is yours. Thanks a lot. And thanks a lot, Oliver and Lee.
Thanks, Giuseppe. Thank you. So I'm, as Giuseppe said, I'm Ben Collins from Queen's University, Belfast, and welcome also from me to the second webinar in the current season of the HUPO ETC series, where we're aiming to take this deep dive on technical background of some of the technologies that many of us are interested in. And so today we're very honored to host Oliver Rather from Bruker Daltonics in Bremen, where he's a research and development manager. He got his MSc in engineering from the Hamburg University of Technology, and over the past nearly 3 decades, he and his colleagues have developed orthogonal time-of-flight mass spectrometers. And importantly, since 2010, this includes the timsTOF product line, leading to many scientific publications and patents. And relevantly for today's audience, actually, Oliver was also awarded the HUPO Science and Technology Award in 2020 for contributions on the TIMS technology. So I think we're very lucky today to have with us one of the leading experts in the field. And I can confirm actually that he's really one of the experts, because as a part of this DIA passive collaboration we participated in with several other labs, I got to visit his lab in Bremen once, and he showed me actually one of the very early prototypes of the timsTOF instrument standing in his lab, which was cool to see. Good. So I think we're aiming for roughly a 45 minutes talk, and then we have some questions and answer after this. Oliver's topic today is the past, actual, and future directions of trapped ion mobility, time-of-flight mass spectrometry. And with that, I would pass the ball to Oliver. Oliver, if you can try to share your screen again. Yeah, it looks good. So I will switch off my video and enjoy the talk. Thank you.
Yeah. Many thanks, Ben, for the introduction, and many thanks to the ETC for having me here. It's always a pleasure to present something at the HUPO. I had some opportunities in the past to do so at the conferences. Yeah, my title of the presentation is here. I need to locate my, So this is the more detailed agenda for today. As Ben mentioned, it will take about 45 minutes, 3 chapters, let's say. First, I will go through, let's say, the timsTOF trapped ion mobility separation instrumentation, and give a short overview of what had been released already, and so if you are a timsTOF user, you can maybe sort where you are and what you can do with your system, especially from the from the different DRA techniques we have over the time implemented on the timsTOF, and also for the future instrumentation we are currently developing. For those of you who can stay until the end of the meeting, I will explain the picture you see here on the right towards the end of the presentation. So starting with the timsMS, I have in the whole presentation not much formulas or theory about mobility cross-section or so. There are many good presentations out there and articles published. So I try to keep it as simple as possible and give you more the big picture, let's say, of what is possible and not diving into technical details. So this first set of slides is maybe the most technical one. And what you see here is a cross-section of the TIMS analyzer. So we have here the analyzer section. We have a capillary where the ions from the source are introduced, and we apply a repulsive electrical field. So here you see the electrical field strengths, and above the zero line means they are repulsive. So ions are stopped in the electrical field here, and the gas is pushing the ions towards the exit of the TIMS analyzer. And if the electrical field strengths and the gas force are in balance, then ions are trapped. That's where the name trapped ion mobility analyzer comes from. And now there's a short animation. So when we accumulate ions, we let them introduced, and you should see now that the bigger ions are stored here and the smaller ions are stored. Sorry, I have to switch on the laser pointer. So now I can point it. So these are the bigger ions, the smaller ions. They are located along the axis of the analyzer, and we can now modulate the electrical field in order to release ions in basically a very flexible manner. So for the elution of the ions, we would now turn down the electrical field, and then in the mass analyzer we see a peak, mobility peak. Yeah. So this stands for a certain mobility, this peak, and after a time we can release the second one, or we can scan the electrical field strength down, and then we would get this mobility peaks of the species formerly stored. And as we in the timsTOF have, of course, also a time of flight analyzer, a quadrupole for filtering, and a collision cell for fractioning. There are a lot of possibilities what you can do. I will go into this later. For now, that's enough, and I want to show you how it's all begun. So there had been an initial publication from Francisco Fernandez Limer and co-workers in 2010, where the first TIMS mobilogram was shown. And this period of time where we had this breadboard or first prototype, and until we launched the first timsTOF product, we upgraded the Bruker Impact QTOF with TIMS analyzer. And there had been like 5 upgrade kits we provided to collaborators like Francisco, but many others. And in this period of time, it's like 5 years, we developed already a lot of methods for the timsTOF. And one is maybe the most prominent one for the proteomics community is this passive publication. Passive stands for parallel accumulation sequential fragmentation. And this is published by Florian Meyer from Matthias Mann Group and in 2015. And this was really a proof of concept paper. So we this what you see here is not that important. Here you see the mobilogram, and it was very manually programmed. So we just could address, let's say, how many are these? Like 4 different or 5 different precursors in a row, but only this, because everything has been manually programmed. And this was just to envision that later, if everything is automated, having a precursor selection algorithm and things like that, that it might be possible to do proteomics here. Here's one other example, also very early before the launch of the first timsTOF, that is from Christian Bleiholder group, from Fanny Caroline Yu, and they got like 2 of these first TIMS cells, and they did run the first tandem TIMS experiments. Oh no, sorry, no, this is CRU analysis. The tandem TIMS comes 2 years later. So this is CRU analysis of ubiquitin, and Christian always did a very good job with his team to demonstrate that TIMS is very comparable to drift tube ion mobility spectrometry. So really, in these early days, people had been very skeptical about this technique, but also from the theory, and if you understand the physics, it's pretty much the same than a drift tube. Yeah, and then in 2016, we launched the first timsTOF, called timsTOF, and that has now a dual TIMS analyzer. So to enable this parallel accumulation approach, we have an accumulation region and an analyzer region to scan out the ions, as I just mentioned. And with this parallel accumulation, we just could double the duty cycle. This instrument generated then mobilograms like this, and going back to the 2010 mobilogram, so it's the same species tuning mixture, and you see in this 5 years of development, the mobility resolution has been improved, but you also see that you now here see the inverse mobility. So there's a calibration applied, and yeah, so that's the progress we made, let's say, in the background without having any system on the market. And that's maybe some of the take-home messages of this webinar, that from the idea to an instrument being sellable, there's in this time a huge time, but yeah, you will see in the course of the webinar that it always takes a lot of stuff to be done before the final user can use it. Yeah, so in this case, it's like 5 years the development took place. And with this first instrument, yeah, we could do a lot. So for example, this was just a measurement of isomers, tree sugars, and you can see on the TIMS is very flexible. That's one of the advantages. You can decide by the ramp speed, yeah, how fast you lower the electrical field strength. You can decide on the resolution. So here we demonstrated that really with a resolving power of 20 to 40, it's not possible to separate the tree sugars in mobility, but if you scan slower, then you see them separated. There are other examples of isometric lipids, and yeah, what was most important is that we also provided a data analysis software, let's say a viewer on the data, where you could see the so-called heat maps, where you see the mobility, the mobilograms, and the map which shows mass versus mobility. I will show that later. And we decided for an open data format. And from my perspective, this was really one of the most important decisions taken, because the processing software, yeah, especially for proteomics, is really a huge effort to add this additional dimension of mobility into the existing algorithms. And many groups in the world, I think in the first year, more than 40 times our SQL or TIMS development kit, software development kit, had been downloaded. So there was a huge interest in the bioinformatics groups. And that was, I think, part of the success that we could launch then a solution for proteomics. And yeah, actually, the timsTOF was kind of successful because it raises a lot of interest. But I remember on the launch event, most people I spoke with, and that had been like 30, found it interesting, but they would not purchase it because the fully automated software is missing. Yeah, so no algorithm to do DDA, no post-processing. So it was, I would say, moderate successful without these tools. But still, a year later, we could launch the timsTOF Pro that had an improved TIMS analyzer, so higher capacity, namely, and we had the acquisition software to do DDA passive. So we had a precursor scaling included, and we could steer the TIMS analyzer synchronously to the TOF and really decide about several precursors per TIMS screen. So we had a very high MS data rate of above 100 Hertz. That time that was really new. And we had also some collaborators who made it for the launch. That was at HUPO 2017 in Dublin, who made it to have a running post-processing software. So here, Peaks and Max Quandt from Jürgen Cox had been the first software tools to analyze the timsTOF data. Yeah, and also then we could release the second passive paper, again, Florian Meyer and co-workers. And yeah, here we could really demonstrate like the protein IDs and which was pretty amazing that time. I know that meanwhile we have higher IDs on the same sample, but that was, at least for us, was groundbreaking performance with this technique. And yeah, so and here I read the note. It was about 3 years after the technical publication where we manually programmed it. So it took at least also 3 years to implement the acquisition and the processing. Yeah, and from this I can go a bit faster through it. In 2018, we launched the DRA passive method, acquisition method, and also a first processing software that was then at that time open source. So Matthias Mann formed in collaboration with Rüdi Abersold Lab and Hannes Röst from University of Toronto. And Hannes and his team really could adapt their open source software at the mobility dimension. I remember that Annie Hart did really a good job to implement all the new stuff into the open source. And so we could launch then at HUPO 2018 this DRA passive workflow. I have here a picture of the EvoSep 1 because that also came out in this year. And together with the team of Oli Worm, we adapted the EvoSep also to the timsTOF. So that was another hardware launch then, let's say, for the timsTOF family. Yeah, and here now I have the citation for the paper I mentioned already, that Christian Bleiholder in the same year had the first publication with the tandem TIMS. So he put together with the colleagues from Bruker Research in Billerica, he put together 2 TIMS in a row and could do CID in between. And there are a lot of papers out. If you look at, if you're interested, you can look at Fanny Liu. She published, I would say 5, 6, 7 papers about the tandem TIMS and what you can do with it. They have also now a second generation of tandem TIMS where they can do UVPD in between. So it's interesting, but maybe not that interested for the proteomics community. Therefore, I don't dive into that. Chronologically, a year later, we integrated the ion source, the MALDI source from the Bruker UltraFlex and RapidFlex into the timsTOF and offered the timsTOF then with a dual source. So we could do MALDI and electrospray actually at the same time, simultaneously. There was not that much use for doing electrospray and MALDI at the same time, but you can, without any mechanical chain of parts, you can switch between MALDI and ESI, and the performance of the timsTOF flex is the same. It had been always the same than for the electrospray version of the timsTOF. So it was very successful also for Bruker, who is the major vendor of MALDI equipment. It was a very successful MALDI product from that moment. And I have here just one of the first papers, or the first paper that is from Jeff Spraggins from Vanderbilt University, Richard Caprioli group. And they really provided the imaging software and programmed the software on their own. So Bruker could, at the launch, not show such images, but what you see here. So this is kind of interesting. This is a lipid isomeric lipids, so having exactly the same mass, but different mobilities, and you see how the tissue image changes. Yeah, so for example, the one lipid, isomeric lipid, is located only here, whereas the other is more located here, and that is really a new capability to the world of multi-imaging. So that was an important milestone, and yeah, from that then. Going a bit quicker through it, we have the timsTOF Pro 2. So Pro, by the way, stands for proteomics, and that has a new TIMS analyzer, and it has also a new instrument controller, which is very important for the workflows I will show in terms of DIA. So we could connect the quadrupole and the TIMS in one FPGA and run it really synchronously. That was important to further improve the duty cycle, but also to enable additional workflows. And also in the same year, we launched the MALDI-2 possibility, that is post-ionization with a second UV laser, and which increases the sensitivity for apolar compounds like vitamin D or other special lipids. Yeah, with that, we can go on. I just want to build up this tree so that you see what the different flavors of timsTOF look like. So the timsTOF SCP is like a third branch of timsTOF. It comes with a little bit different form factor, but it includes an additional differential pumping stage. So we could, at the source, we could introduce more gas into the system, pump it away in a so-called single cell cartridge. So SCP stands for single cell proteomics, and it increases the sensitivity of the timsTOF Pro 2 by a factor of 2, which is huge if you want to go to really low sample amount. And yeah, and then finally 2020, so we are close to today, we had a next generation TIMS analyzer and introduced it in both systems, in the timsTOF Flex and also on the timsTOF, which is now called HT. With that, it has a new digitizer, so both systems have a new digitizer, which increased dynamic range of the detection system, both on the digitizer side, but also on the detector, because we can now amplify more in the digitizer and less on the detector, and that releases, let's say, the load from the detector. And yeah, for the MALDI, there was an increase in spatial resolution from 20 micron to 5 micron, which is also, of course, important, and also needs a high sensitivity system, because the smaller the pixel is, you acquire the more ions you need out of it to get a clear picture, let's say. Yeah, and then finally, last year, we launched the timsTOF Ultra. It was a further development of the timsTOF SCP. So again, higher sensitivity. And yeah, with this, the timsTOF family as of today is complete. And what I want to point out is that Bruker has always a pretty, I think, user-friendly upgrade policy. So in principle, you could upgrade a timsTOF from 2016 to 2024. It's here a couple of steps, and I think meanwhile we discontinue upgrade packages here in between. But if you had this old system and always purchased, of course, the upgrades, and then you could have still a state-of-the-art instrument, and that is true for all branches. There are some restriction here on the MALDI side. So the first timsTOF Flex systems could not be upgraded to MALDI-2 because the window for the second laser was missing. So there are some technical boundary conditions where you could not upgrade, but we always have the policy, and I appreciate that our management agrees to it, that we could upgrade customer systems, because at least for me as developer, it's leading to a better collaboration and interaction with the users. Yeah, that's the first part, just giving an overview. And now I will start again with an overview for DIA passive, or generally data independent acquisition, and will explain you some new developments which are close to be released for the DIA on the timsTOF. So first of all, I want to point out to this publication. It's from 2020, a group of Chinese authors around the Westlake University in Hangzhou, and they really assembled all the publications around DIA and separated them in DIA acquisition publications, software tools, and analysis tools. And I have to update this a little bit because in the past 3 to 4 years, it's happening a lot, let's say, in DIA. I would say DIA has become more like a standard for proteomics analysis compared to DDA. And yeah, looking at this, first of all, I added here like 5 yellow dots. Yellow means it's the software is supporting the Bruker timsTOF Pro. Yeah, it says here in the publication timsTOF Pro. And you see that meanwhile, all major software tools, especially Diane, Skyline, and also DIA Empire, Peaks, I mentioned already, it has been from the beginning, all software tools, let's say third-party software tools which are not related to a certain vendor. Yeah, then of course Bruker timsTOF is not supported, but yeah, this is really well accepted, let's say, in the post-processing developer community. And I add another 2 systems, software tools. One is MaxDIA from Jürgen Koch's group, published in 2021. And then I want to add the Bruker vendor-specific tool. It's based on Diane, and it's also available, of course, with the timsTOF. And on the acquisition scheme side, I also want to add one publication, especially because it's adding here on the very top. And that is, I think, a very remarkable paper from Cherokee Haugland Heiser from David Klemmer lab. And she did already 2000, so 3 years before the first, or let's say then the second DIA publication came out. She already demonstrated parallel analysis of, in this case, I think it's 5 peptides. So it's a 5-peptide mixture, and you can read out here the fragments of each peptide in these lines. And this line here is the mobility, and this line is the mass. So I added it for the reason that this is exactly how the timsTOF is operated today. Yeah. So this is what we would now call a heat map, and here it's the drift time and flight time, but it's basically mass and mobility, what you see here. Yeah. Maybe some remarks to the other milestone presentations here. So shotgun CID is really one which is very important, and it's from Pervine and David Gottlieb lab. The DIA von Venable is, so he's from John Jade's lab. It's a Scripps Research Institute. And yeah, this is a publication from Matthias Mann group. SWOS is maybe the most prominent DIA or most known DIA method developed at the ETH Zurich from Rudi Abersold group. And yeah, so Sonar is from Waters and so on. It's now scanning. SWOS is more SciEx now. And here we have the Bruker publication I just mentioned, the DIA passive. But what I want to do is I want to sort these different acquisition techniques a little bit. And I marked them by color here for you. And first of all, I mark all publications which do full mass DIA, I call it, so that which have no quadrupole isolation. They just apply collision energy. So at Bruker, we call it broadband CID. So you just switch collision energy on and off, and then try to analyze the data in the post-processing. So these are these 3 publications which are doing this. And then the majority of publications are about what I call selected mass DIA, like this was, where you use the quadrupole to increase the selectivity. So you step through or scan through a quadrupole window and get higher specificity, higher selectivity, and therefore can analyze more complex samples. And these two basic or fundamental differences can be expanded and could be, let's say, complemented by ion mobility. And so I have two new colors here. And if you look, this very early paper I just mentioned, and the Waters HDMSE, they make use of mobility separation, but without quadrupole usage. And really at that time, and I think it's still the case, the Bruker had been the first group, and together with Matthias Mann, who combined both so mobility separation and selected mass. And that is, as far as I know, still really a differentiator of the DIA on the timsTOF. Yeah, so this quick summary, why to add the mobility separation to DIA: it increases selectivity, it reduces the FDR when you make use of the collisional cross-section information. So for each species you detect in the DIA data set, you automatically also get a mobility or collisional cross-section information. And at the beginning, also in Matthias Mann group, there was a publication. They just built up a library where I think it was more than 100,000, maybe even more than 1 million. I think the goal for Matthias was to really have 1 million of peptides in a database with collisional cross-section. So like a spectral library, including collisional cross-section or mobility. But meanwhile, I think that is no longer used because the tools like Diane with the neural network training, they can predict the mobility pretty good. Yeah, they predict actually also the spectral library. That means spectral library means you have different intensities on the fragment. And that is important for library matching in DIA, that you know the probability or the intensity ratios of the peptide fragments. And that is really one of the major differences today. I think they call it direct DIA. I don't know the term, but Diane, I think, was first to introduce it, this direct DIA, and Spectronaut has it, and I think many other tools will also have it, that you now use a neural network approach and a huge training data set, and then you can just by the sequence of the library peptides, you can in silico predict the spectra. And that means that you these days no longer need to do a DDA with maybe LC fractioning, so huge effort experiment to create your library. So that's really also a game changer, let's say, on the DIA acquisition. Yeah, and with the DIA passive, which I will explain in the next slide, we also increase the duty cycle compared to the selected mass DIA, and then I will explain how this works. So in the rest of the webinar here, I will use this heat map only. This is just more a symbol, let's say. You see the mobility on the y-axis, the mass on the x-axis, and typically these are the doubly charged, triply charged, and highly charged peptides, and this is singly charged species, also contain, of course, a lot of peptides, but normally we target here this region for proteomics. And here in the webinar, I simplify the TIMS operation. So the red line is now a symbol, let's say, for the electrical field strengths I mentioned. And yeah, what we do is we scan the electrical field strengths, and then we elute, let's say, row by row the peptides, and they undergo, let's say, collisional fragmentation, CID, collisional dissociation in the collision cell, or selection by the quadrupole. So the TIM scan is now just depicted like this. So we have a starting point and we have an end point for the TIM scan, for the electric field strengths we scan. And a typical scan time is like 100 milliseconds. It's very flexible, as I mentioned, but just here to make it a little bit more practical, I put in this timing here as an example. And if you now want to do DIA on the timsTOF, I overlay here a region. Light blue is now, this is, by the way, from the control software of the timsTOF, the editor where you can select the region you want to address. And in this case, if you want to address these regions, then the DIA passive works like this. So you use the quadrupole to select a mass range. So a mass range, or a 25 Dalton mass window, is depicted here in green, and you see the red scan range of the TIMS. And if we now start the TIMS scan in slow motion, we address the peptides on this red line. And once we reach this point here, where the blue programmed area ends, the quadrupole jumps to here and scans the next and the next. And then we can, so this is now 100 milliseconds, and then we can continue with the next 100 milliseconds, addressing the next part of the error, and so on. So I think the animation speeds up now. So in total, it takes us 800 milliseconds to go through all of these regions. That is a typical method on the timsTOF. But that means it's compared to the selected mass DIA without mobility separation, it's 3 times faster, because we jump, as you remember, we jump 2 times, and in 100 milliseconds, we address already 3 25 Dalton mass windows. So we have higher duty cycle, and we have the additional benefit of the selectivity I explained with the predicted mobility. So this is the technique we introduced first. And meanwhile, there are a lot of groups working with this, and I want to highlight some of the publications coming out with this technique. First one is a pretty recent publication from Patricia Skrovonek from the Matthias Mann group, and she and her co-workers had provided a Python tool which defines the window size, so the window width, based on the density. You're here on this figure from this paper, you see the density of the, I guess it's HeLa species here, and the window size is broad here at the beginning, where there are low, or a smaller number of peptides in this region, and then the window size shrinks down here to the middle, and then it becomes broader again. This gives you an additional duty cycle approach. Then I have a presentation here from Vadim Demichev lab, Lucas Cheville. This is also most recent publication on bioRxiv 2022. They called it slice passive. The good thing is, if Vadim is involved here, you always get also a Diane version, which can handle the data acquired and is kind of optimized. And I have a couple of other examples here. This is from Nikolai Slavov lab, Jason Dirks, and he is doing kind of interesting technique, doing multiplexing on DIA. So they use like 3-plex Amtrak reagents here. And that is also a new approach. And again, I think Vadim is here on the list of authors. So you get directly an adapted Diane version, which can retrieve or make use of the correlation of the differently tagged peptides, and that is of course a benefit. Another publication, Speedy Passive, from Markus Reiser group, again with Vadim here on the list of authors, and also Lucas. And with this, I want to switch gears and show you something new. And at Bruker, we programmed already the acquisition scheme, or had programmed it since 2020. And maybe you have not heard about it right now because it's not yet, let's say, usable for the end user, so for the proteomics community. What we change is that we go from this acquisition scheme to that one. Yeah, so we can now scan parallelograms and program parallelograms. We could even program trapezies, but currently we are using the parallelogram because the calibration is for the moment only provided for this kind of scanning. And if we want to address such a area here of the heat map, then we again add the quadrupole isolation window, but we don't scan now in this direction and have the jump, but we move the quadrupole window together with the timscan. So that looks like this. And as you can see, we now address, let's say, the peptides on this red bar. And because it's like diagonal in the heat map, I named it here, and I think we tend to name it diagonal DRA. And yeah, if it continues, the quadrupole jumps back, and then the timscan, second timscan is gone, and so on. So we address the blue area, and if you have noticed, the area of peptide content is actually namely the same than on the former DRA scheme where the quadrupole jumps, but we address the same area with less timscans. So in this case, we just have, in this example, let's say, we just have 6 MS timscans. I always add a survey scan in MS. So we reduce the cycle time to 700 milliseconds from 900 to 700, which is again a plus of 30% in duty cycle, and it's like now 4 times faster than the selected mass DRA alone. And yeah, with this additional duty cycle, you could, for example, reduce, if you can make the chromatography faster, or you reduce the window size to increase selectivity. It's all very flexible. And yeah, as I mentioned, since 2020, some collaborators in the bioinformatics community work on processing tools, making use of it. And one very prominent collaborator is Stefan Tänzer and his group from the University Klinikum in Mainz. And he is proposing, I would say it's even an additional dimension. So what Stefan Tänzer recognizes or envisions, he filed a patent already in 2020. So right before we provided this new acquisition scheme, and he is suggesting that you can do on each, and I focus now on this chart of this figure, each fragment, yeah, in the DRA has a certain pattern, yeah, like this diagonal pattern, and this pattern is highly related to the precursor. That is because the precursor is scanned by the quadrupole, and the scanning quadrupole is, let's say, I want to make it here really easy, the explanation. So the scanning quadrupole is introducing a pattern which is related to the precursor. So, and if you see such fragments, which based by an AI algorithm and also again machine learning, could be correlated to each other. So you see a high intense fragment and a very low intense sparse fragment, and you could calculate back to the precursor mass, and that is within the range of +-2, +-1 Dalton. That means we have a selectivity on this experiment, like in DDA. Yeah? We have a 1 Dalton mass isolation window just calculated out of this diagonal DRA scan, and that is really, yeah, I would say it's adding a dimension. It's adding the precursor correlation dimension, even if it's mathematically not a dimension. And with this, Stefan Tänzer can directly retrieve DDA-like spectra out of the data set, out of the DIA data set. So really, you don't no longer need to have a spectral library. You don't need any library. You can do all the applications where de novo sequencing is required. And that works pretty good in this bioRxiv publication, Stefan demonstrated that the spectra quality is much better than on a comparable DDA run. Yeah, so really this will open DRA to let's say additional set of applications. So that is coming. It's not yet published, the software, and actually Bruker is working to introduce this technique, maximum information DRA or media passive, into the proteoscape software. There's another very interesting publication named synchropassive, again from Patricia and Matthias Mann group, and she is using the same technique, so the diagonal DRA, and she is, I put in this picture, this figure here because it's very interesting. So this is like DDA acquisition scheme. You have make use only on small spots, make use of the peptides with the she's calling it here current DRA. There you have the scanning TIMS and this the quadrupole selection, and then jumping here, you see this is the peptide content, and if you scan along this diagonal, you see it's much more peptide content, and these bars here show actually the difference. Yeah, it's 3 times higher fragment contact in this synchroscan. Also, Patricia is introducing, and her group, I think from the informatics, is namely Sander Willems and Georg Wallmann. They also using kind of precursor correlation, so they can filter, let's say, the resulting fragments and increase the probability for the library matching. It's still, I would say, more a classical library matching approach that will not generate DDA-like spectra, but also very interesting thing. And here I want to really encourage you to look for upcoming publications or releases for alpha DRA. That is the tool Matthias Mann group is developing. For Spectronaut, so Biognosis is also working on a updated Spectronaut version, which can make use of the diagonal DRA, and it shows already a prototype, showed very promising data with faster cycle times and increased ID. That will be for sure released around ASMS. So I think it's a good practice of Biognosis to release Spectronaut just in front of ASMS, and that is the plan here, to then also provide a tool for this diagonal DRA. And the Bruker proteoscape, the release date is not clear yet, but it's also, I think, to come in the next couple of months. So with that, I end the part of the DRA. And now we go to the future of and current R&D work at Bruker. And I have named here this is how AI, like OpenAI ChatGPT, would illustrate the timsTOF. And then I tried another illustration of a future timsTOF that looks like this. I think the AI is not yet there, but those of you who have maybe seen recently the announcement of OpenAI Sora, which can generate videos out of text input, that's really kind of fascinating and terrifying at the same time. But maybe the future of mass spectrometry development will also go in that direction. Who knows? At the moment, I cannot imagine. You see, it's more like funny than real suggestions here. But anyway, what is coming from the Bruker hardware groups, and I just want to acknowledge that we have meanwhile hardware development, or we all had all the time also in Billerica, where Mel Park is heading the R&D group, and so close to Boston. We have the site in Verlanden now, and we have a pretty new site in Essence. So we also globalize kind of R&D work. And one very interesting approach I will show you now. Actually, it goes back to a patent also from Mel Park, Mark Ridgway, and Desmond Kaplan from 2011. So the idea doing this is not that new, but meanwhile we have first prototypes running, and it's really looks promising in my point of view. And this is the heat map I've shown with this, let's like symbolic TIM scan in 100 milliseconds. And this time we operated differently. We just would apply electrical field by year. So a pseudopotential, no, not a pseudopotential, an electrical field strength. And if we would do it at a certain voltage, then what would happen? The low mobility species, which are here in the upper region of the heat map, they will pass the TIMS analyzer, and the higher mobility species are trapped. So we have a first TIMS mobility low pass. So low mobility species, higher mass species will be passed. And here at this position, let's say, we could add a second TIMS mobility low pass with a slightly different voltage. And doing this, again, the low mobility species will pass, and in this case will be discarded. And what will happen is that we trap here a gas phase fractioning. So what we have designed here is kind of a gas phase selection. And with this, we could, for example, pass it to a third TIMS stage and do mobility scan here, for example. Yeah, but this is not the envisioned use case. I will show you now based on this principle. So I will call this now, these first two TIMS mobility low passes, I will call TIMS mobility filter, and the third TIMS cell I will call the TIMS mobility analyzer. Yeah, having this definition, I can show you some new workflows we want to implement. And so we have now the filter here. Remember, we can select a fraction of species out of the heat map, and we have the analyzer here. And what we propose to do is then doing DIA passive with fractioning. In this case, we would discard the species here and then transfer one selection or one fraction, and then we would apply the standard diagonal DIA TIM scan, so quadrupole isolation, and we would scan here. And if the quadrupole reaches that position, we would step by step pass the other fractions seamlessly. So the TIM scan will remain the same. So the good thing is data processing will also remain the same. So in this case, we have the processing software right away. And we have another capability here, and that is parallel accumulation. If you remember my picture of the TIMS filter built out of two TIMS cells, the second one acts as an accumulator. Yeah, so we accumulate always in second, and we scan in the third, and this works like this then. So we do accumulation here, transfer, scan, and accumulate the next segment, accumulate the next segment. And once we are at the end of the first diagonal scan, we have accumulated already the first fraction. So that means we can seamlessly accumulate in parallel to the sequential fragmentation, which then gives us again high duty cycle. And yeah, I think I just repeat the animation here to see the accumulation on the left and the scanning on the right. And so what are the benefits of this mode? So what we could do is we could convert the high sensitivity of the timsTOF Ultra, to higher dynamic range and deeper proteome coverage. Yeah, so from the timsTOF Ultra, we can make use of this technique already for sample amounts above 20 nanogram. Yeah, on 20 nanogram or lower, so the single cell application, it would not make sense to apply this technique. But if you apply like a microgram of sample, if you have enough sample amount, then you can make use of this technique, and you just, in a best case, you automatically adapt the size of each fraction to the sample amount. Yeah, in like a not an automated gain control, but like in an ion charge control realized by this fractioning in the first TIMS filter. So this is something promising. We will do some proof of concept measurements had already been done, but we don't have yet the acquisition software to run everything over an LC run. So we only can do proof of concept experiments at the moment. But another very promising operation of this TIMS filter is what I called here PRM. And PRM passive is already possible with the timsTOF, but we would add a special mode for low abundant species. So for example, if you in a targeted approach know that here is a peptide of one protein of interest with very low abundance, which we not can quantify on a standard PRM experiment, then what we could do is that we discard the upper and the lower region and actually operating the TIMS filter with static voltages, what I've shown, will increase the mobility resolution of the TIMS. Yeah, scanning very slowly increases the mobility resolution compared to fast TIMS scan, and having it at static condition gives you highest mobility. So at least 200 mobility resolution should be possible, maybe even higher. So Francisco Fernandez Lima showed resolutions up to 450 on a modified TIMS analyzer. But yeah, we are not yet there to spec this, but we could have this narrow isolation, and then we would accumulate. Yeah, we accumulate just this fraction, and we can accumulate over a pretty long time. So for the timsTOF Ultra on, for example, plasma, we run with 5 milliseconds accumulation time, and here you could run with like 100 milliseconds, which is still fast, but you would have a factor of 20 increase in sensitivity and protein depth coverage for selected targets. And yeah, if we have this species now accumulated, we can apply the quadrupole filter, and as it is targeted, we can select the window size. We could go down to 1 Thomson if necessary. If we want to have the isotopic pattern, then we make it a little bit broader. But this really, I at least, I'm pretty sure that this will give very good PRM performance on this timsTOF. And yeah, you see, we will increase the mobility resolution at least by a factor of 4. So higher selectivity, we can combine it with a narrow quadrupole window, and we could even combine such PRM targets with DRA, diagonal DRA. But I think a general PRM approach where we typically run like 80 targets in a classical, let's say, PRM, where we address a lot of targets in a standard TIMS scan, and then we could add like 3 high sensitivity PRM targets with making use of the mobility TIMS mobility filter, and this will give us 1 second cycle time. So let's say 83 PM targets plus an MS per second. That should be easily possible. And of course, you can have it flexible for medium abundant peptides. You can reduce it and then address more. And so it will be flexible, that's for sure. Especially on PRM, you have all the possibilities. And finally, I want to show you a last usage, or a third usage of the TIMS mobility filter. And that is excluding high abundant species like the high intense albumin peptides from neat plasma. And what we would do is we do a survey scan, so the MS scan, and have a detection of the high mobility of the high abundant species, and we would dynamically filter them out. So in this case, yeah, it works like this. You can imagine we scan in diagonal DRA the first fraction of the heat map, then we stop here, let's say, and then we could decide now the high intense precursor is eluting. We could either skip it, so jump above this mobility region, or we scan it, but with a very short accumulation time. So the filter has normal accumulation time here in this region, like 5 milliseconds, and then we have even lower or no accumulation time on the high abundant species. Here it's still in the heat map, and then we scan with another short accumulation time the rest of the heat map. And yeah, with this, we have, first time in my presentation now at the end, we have a slight disadvantage in duty cycle because we need 2 accumulation times. So if we have one precursor which we want deselect, filter out, then we need to accumulate 2 times. And if we want to exclude, like in this example, 4 precursors, we need to accumulate 5 times, depending on the distribution of the precursor. We can do parallel accumulation, but if they are distributed not evenly spaced, then we will lose, in worst case, for each excluded precursor, the accu time. And doing some math here for this example, if you want to exclude 4 targets, we lose about 80% of duty cycle, which is still great. And further than that, Aaron Pansek from our research group in Billerica, together with Ben Jones and Mark Ridgway, they have already shown that they see a huge increase in identified proteins out of neat plasma with this technique. And with this, I'm at the end of my presentation, hopefully kind of in time, and I exceeded a little bit. And I would end with the acknowledgement, and I'm happy to answer questions.
Fantastic. So thanks very much, Oliver, for this very deep dive on the technical aspects of TIMS. We do have a few questions. I don't know if you can see the Q&A, or I can try to summarize for you. So the first one concerns the MyDIA PASEF. So you mentioned Proteoscape software. Do you think there will be other software solutions available, in particular open source software solutions like Skyline? Are there any activities on this side planned?
Yeah, actually, I do not know about Skyline. I hope that the Vadim Dimitrov group is also working on a processing software. Mm-hmm. Maybe also for the media. I mentioned that is a patent of the University of Mainz. So I think that has to be negotiated with Stefan Tänzer or the university to get a license. I'm not 100% sure how this happens, but I really hope that. So the diagonal DIA I showed is already since ASMS last year included in the acquisition software. It's called VistaScan there. And I think that users will acquire data, and all the bioinformatics groups can acquire data if they have access to a timsTOF or a collaborator. So mm-hmm. I hope that this will take place, and that all other tools and vendors of processing software will jump on this. Maybe they need to be convinced by the protein performance in the end.
Yeah. Okay, good. So, and then the second question is also about the sort of diagonal schemes. Whether does Oliver think that these should have utility in small molecule applications, kind of similar to PASEF, which was originally, I guess, developed for peptides, but then implemented for lipids and so on. Do you see such thing happening for the diagonal schemes?
Yeah, definitely. So I knew that our applications group found already its advantage to use it for lipidomics, and especially the media or MyDIA, how you termed it, that is capable to do DDA spectra retrieval without spectral library. So you can do any application with that and still get DDA like spectra out of a DIA run. So that should work. Not sure if the software supports it. So really, the software is maybe you have recognized that Stefan's tensor, and Bruker started 2020 to implement it, and it's maybe now close for release, but it's high effort, I would say, and it's the group of developers is not small there.
Yeah, yeah. The next question is also about small molecules, and especially less than 150 m/z. Is there any development that might improve analysis for these small molecules using TIMS, like the small?
Yeah, actually, we are working on improvements here, but it's too early to give any concrete statement. We know about this and that you actually lose duty cycles. So we have this, I think we call it TIM stepping, where you have a very small molecule scan and then another scan on higher masses. But then you lose 50% of the duty cycle. And for most applications, I think for small molecules, it's used from time to time. But yeah, we know about this and yeah, but I cannot announce any concrete result or development here.
Okay, very good. Fourth question relates to library matching from DDA to DIA analysis. How important is it to have the same LC conditions? Is there some flexibility there?
Yeah, I'm not expert on this. Maybe rather you, Ben, but I would say the DDA generation of a library is no longer that important. So the colleagues from Biognosis, they mentioned that you maybe get a low single-digit percentage increase if you take the effort and generate on the same system with the same LC a DDA library. But the predicted library, or I think it's called direct DIA, at least in one tool, that is most of the time used and for everyday work, especially if you run DIA across different instruments, maybe even from different vendors, then the direct DIA approach is much more advanced and easier to integrate.
I agree with this. I mean, I think you can still top up a little bit with these larger libraries. And in terms of the chromatography matching, many of the softwares have now nonlinear alignment in the retention time space. And I think this makes a big difference if you want to match across LC conditions that are somewhat different. Although the further you get away, the less good it is. I would put it like this. But I kind of agree, Oliver, that it goes in the direction of direct analysis. Okay. Do you think it's possible to create a type of spectral library for the 14 more abundant proteins using the dynamic mobility filter? And this person even proposed a name, digital depletion, he wants to call it, David Gomez Varela.
So I actually, maybe I do not get this fully. So there are 14 abundant proteins.
I guess he was talking about the plasma data that you showed towards the end there.
Yeah, I excluded 4 of them. I think identifying them is not that much of an issue. Yeah, they will be low abundant species on the tailing of the chromatography. So typically they tail a lot, and I think we identify them all the time. Problem is that they suppress other ions, other low abundant species with the same mass and mobility, and here you really the deselection work pretty well on a few of the albumin peptides. This is maybe kind of what I just mentioned at the beginning, where Florian Meyer and colleagues did program it manually. That is the status now. Yeah, so really they programmed manually to exclude the high abundant albumin peptide species and showed great progress, but now all the software, acquisition software, need to come together and do it then in an automatic manner.
Yeah. Okay, David, I don't know if we answered the question. You can write a clarification if you like, but I think maybe. And then, so the last one, people keep adding questions, so I say the last one again. So with respect to the fractionation, how do you keep track of calibration in the IMS dimension? Does it become more challenging, requiring more evenly spaced calibration solutions that would show up in all fractions? So how do you calibrate with this fractionation in ion mobility dimension?
Yeah, maybe just one comment to the former question. I like the digital depletion term.
It's a good name.
Yeah. Yeah, so actually calibration is not affected for 2 of the 3 things I propose. If you have this third TIMS analyzer, where you do the fractioning, let's say very systematically, and transfer the fraction right in time for the analyzer scan, then you just keep the calibration of the TIMS analyzers. Of course, we need a calibration of the TIMS filter. That is anyway needed, yeah? So the static calibration of the TIMS filter, that is an additional calibration we have to implement. That is possible, but it's not yet seamlessly implemented. One of the tasks we have to do, of course. And for the same as for the PRM approach I have shown, there you just need to calibrate the filter, and then you have the mobility of that special target species. The classical or the higher abundant PRM targets will be run as normal, and then we add some species. I had a nice conversation with Tejas, I think the R&D manager of Biognosis, and he said it's not any problem to include those targets into their PRM software Spectrometry. So that will be very easy. So I guess we get it right away when we have the acquisition scheme ready. And yeah, I guess that will then also be the case for the other bioinformatics platforms. So calibration there is I would say it's some work for the filter calibration, but it's not challenging or not risky or what. Yeah, I think it's just work to be done. For the third mode, there it might happen that calibration is more challenging because we need the service scan directly giving you the same mobilities as then the fractions, and stopping and starting the TIM scan, for example, if we need to, or jumping across. What we did so far is that we calibrated both parts of the scan separately, and actually it's one and the same calibration. If you have the same scan speed on the TIMS, then the calibration can easily be transferred. Only if you change, let's say, the slope of the speed, then you need, as of today, recalibrate. Christian Bleiholder published an approach where you can have, how is he calling this paper? Is about unified calibration, yeah. And then he with a set of experiments, he could calibrate the TIMS analyzer independent from the slope, and so that might be some approach. But yeah, that's definitely a question which needs an answer.
Okay, and just maybe one further question from me on that is, because the hardware, you need serial TIMS analyzer, I guess, to make this work. As in, are we likely to see new hardware coming to support this at some point, or what's your feeling about that?
Yeah, so at least the TIMS filter would fit in the timsTOF Ultra or in the timsTOF SC. It would fit in any timsTOF.
So it could be an upgrade, you mean?
Yeah, so that could be an upgrade. I would say it makes only sense for the timsTOF Ultra because you need the high sensitivity in order to have the short accumulation times. If you would do it on let's say in timsTOF HT or older timsTOF, then you would lose duty cycle by that, or less gain, let's say, in filtering. So the PRM workflow definitely could be an upgrade. I don't know if that is decided to be an upgrade or if a new product will be released. We have, of course, a lot of other components in development. So maybe we release a new product and combining a couple of components. But yeah, in the past, we always offered also an upgrade if possible. For the other two scan modes, we need a third TIMS analyzer, a third TIMS cell. Theoretically, it fits in the Ultra because we have this single cell cartridge that we could integrate another TIMS, but that's not the best performing design, I would say. So possibly we will come up with a new design on this TIMS filter.
Okay, great.
Yeah, but
okay,
it's nothing I can stay for granted. Yeah, it's not yet decided. It's still in development. So
Good. Okay. Well, then I think we can start to finish up because it's getting a bit late. But then we finish with maybe one controversial question, which you can answer or not. But some in the chat would asking questions about comparisons between timsTOF Ultra and, for example, Astral. And there's also a proposal to have a debate at ASMS between the some kind of face-off between these two. So, do you have any general comment about the comparison between these two type of instrument?
Yeah, of course, we look closely what the R&D guys at the other side of the River Weser are doing. So they are also located here close by in Bremen. That's what I mean. And yeah, it's a very interesting instrument, of course. And I would say it gives surprisingly from the publication I see and from users, it gives surprisingly good results. Actually, I see some some compromises on that system, but as it performs good, it's a good combination. And yeah, really, I think for the community, it's good if there are as many as possible different hardware configurations competing, and that is also for us a nice challenge to have.
Okay, good answer. I think we can wrap up there. So, Giuseppe, did you want to say something?
Yeah, I would like to thank Oliver. Thanks, Oliver, for actually this great overview on the history of TIMS and also showing us all the different flavors of the teams that have been developed. Also, all the participants has been a lot of question actually. Maybe I might ask just last one, Ben, just before.
Sure.
So, Oliver, I was thinking if you could actually tell us more about some application of the teams going towards intact proteins or even complexes. Do you have...
maybe you have heard about, I think we had the team from Athens around Dimitris Papandreou at the ASMS in our group. That is a former Pharmatech, or we call it now Bruker Pharmatech group. And they developed the so-called OmniTrap. And I think it's no secret, we are working on integrating the OmniTrap into the timsTOF. And that will give us great new fragmentation techniques, all what we call EXD plus UVPD and other things which are possible in the OmniTrap. So that will be, I think, really a great addition for the intact protein community. But we are also working on improvement. We have an upgrade for the timsTOF Ultra, where you get way improved desolvation, which we currently test with collaborators. So yeah, there's also a lot of going on the intact protein complex or antibody application side.
Thanks a lot, Ben.
Fantastic. Yeah, thanks very much, Oliver, and thanks to all the participants. So I think we can close it there. I think the next webinar will be in March, Giuseppe, right? And the topic will be reverse phase protein arrays, if I'm not mistaken. So watch out for the announcement for that. Fantastic. Thank you very much. Then we'll end it here. And thanks again to everyone. Bye-bye.
Yeah, many thanks to the audience for attending that long.
Thank you.
Yeah, see you soon and
bye.